Welcome to The Deep Dive, the show where we cut through the noise to get you to the absolute core of critical knowledge. Today, we're plunging into a topic that couldn't be more urgent: the undeniable reality of climate change and, well, the central role our energy system plays in it.
It's huge, yeah.
Absolutely. And just to underscore that urgency, the World Meteorological Organization confirmed 2024 as the warmest year on record. It's actually the first to exceed 1.5 degrees Celsius annually.
About 1.5 mark.
It's not just a statistic, right? It's a global wake-up call, demands our full attention. So our mission today is really to give you a shortcut, a way to understand the cutting edge of renewable energy research. We're diving deep into this massive, really crucial study called Technologies, Trends, and Trajectories Reviewed in 100% Renewable Energy System Analyses.
That's the one. Quite a title.
It is.
Yeah.
And it's not just any paper. It's a systematic review, looked at over 1,000 research articles. It gives this unparalleled look at the global effort to transition to renewables.
A huge undertaking.
Exactly. So think of this deep dive as your guide to that roadmap for a 100% renewable world. We want to reveal the dominant technologies, maybe some surprising gaps, and what it all means for our path forward. So, okay, if the energy system is at the heart of the climate challenge, what does that big picture look like for the researchers? Why is this 100% renewable goal so critical?
Well, that's the foundational question, isn't it? I mean, our energy system is, without doubt, the #1 source of greenhouse gas emissions.
Right.
This study points out that global net anthropogenic GHG emissions actually rose by 11% between 2010 and 2019 alone.
Wow, rose. Even then.
Yeah. And this isn't just about, a warming planet in the abstract. These emissions are deeply impacting land, disrupting food systems. We're pushing past several critical planetary boundaries. It's a profound threat to human civilization itself.
That's really sobering. So against that backdrop, this idea of a 100% renewable energy system isn't just ambitious, it feels essential. What exactly does that mean for the researchers in this study? How do they define it?
Basically, it's an energy framework where all the input comes from naturally renewed resources. So, solar, wind, hydro, bioenergy, geothermal, ocean energy. The usual suspects.
Okay.
Now, for the purposes of this massive review, they were pretty practical. An article got included if it looked at an energy system with at least a 95% renewable threshold in at least one key sector.
So 95% was the bar for inclusion.
Yeah, that 95% mark is kind of a pragmatic recognition. The goal is 100%, obviously, but many studies are tackling that near total transformation, and they wanted to capture that work too.
It's fascinating to see how this field has grown. I mean, it wasn't always such a hot topic, right?
Oh, absolutely not. The very first article, explicitly on 100% renewable energy systems, that was 1975. Sørensen, looking at Denmark.
75.
Yeah. Then you had some early work for the U.S., Lovins in 76, and a global look from Sørensen again in 96. But the real boom, the exponential growth, that's really been in the last 15 years or so.
Right.
This study found that by 2021, we were seeing something like 200 articles published in just 1 year.
200.
Yeah. That surge, it's a powerful signal, increased global focus, real investment in trying to solve the climate crisis with renewables.
So with all this research happening, how are scientists actually building these future energy worlds in their models? What are the tools, the approaches they're using?
Well, there are two main ways, really, that this study identified. About 68%, so the majority use what's called an optimization approach.
Optimization, okay.
Yeah, think of it like a super smart algorithm trying to find the best solution, the most cost-effective or maybe the most efficient energy mix to meet demand under certain constraints.
Got it. And the other approach?
The other significant group, about 27%, used a simulation approach. These models are more like virtual test runs. They explore how an energy system would actually behave under various specific conditions or maybe different policy scenarios.
So like what-if scenarios?
Exactly. What if we build this much wind? Or what if this policy is enacted? Both approaches are vital, but they give you different kinds of insights into our energy future.
That level of detail sounds powerful. But it makes me wonder about the bigger picture of how they see the transition happening. Are we modeling the whole journey step by step, or just looking at the final destination?
You've hit on a really critical distinction there. A big chunk of the studies, 73%, used hourly time resolution in their analysis.
Hourly? Why is that so important?
Well, it's not just a technical detail. It's actually a huge shift. The core insight is this. Without hourly data, you're kind of flying blind when you're dealing with variable sources like solar and wind.
Right, because the sun doesn't always shine, wind doesn't always blow.
Precisely. You can't really understand how much storage you'll need or accurately predict grid stability without looking at things hour by hour.
Hmm.
It's the difference between like guessing and actually engineering a reliable 100% RE system.
Okay, so it sounds like researchers are getting incredibly precise with the snapshot of a future system, but the study also points out something interesting. 77% of articles focused on overnight greenfield modeling.
Yeah, that's the term.
So that's basically picturing a future year, say 2050, as if the renewable system just appeared, fully formed.
Pretty much, yeah. That's the idea of overnight greenfield.
Whereas only 23% actually analyze transition pathways, modeling the steps over many years, like from 2015 to 2050.
Yeah, a much smaller fraction.
This feels like a crucial point. What are the biggest risks we run by not modeling the actual journey to 100% RE more often?
That's a great question because it really highlights a potential blind spot, doesn't it?
Yeah.
The immediate risk is, well, we generate these technically feasible plans on paper that might be utterly impractical to actually implement in the real world.
Makes sense.
Transition modeling is just harder, it's more complex. You need projections about how technologies will evolve, how consumption trends might change, policies over decades. By focusing mostly on that single future point, we might be missing the practical step-by-step challenges.
Like the messy middle bits.
Exactly, the messy middle.
Yeah.
And the critical investment decisions needed along the way to actually transform our infrastructure. It's like, having a perfect blueprint for a finished house, but absolutely no construction plan to get you there.
And it seems this focused approach also extends to which parts of the energy system are getting studied. This study found something pretty stark. The power sector was looked at most, appearing in 99.5% of studies.
Almost all of them.
And it was the only thing analyzed in 47% of them, just power.
Yeah, nearly half focused exclusively on electricity.
In contrast, only 30% looked at the full energy system, power, heat, and transport combined. What are the implications if almost half the studies are just looking at electricity in isolation?
Well, the implication's pretty clear. We risk overlooking crucial interactions. I mean, a truly holistic energy transition needs us to integrate all sectors. That's what we call sector coupling. So if we're not looking at how, say, widespread EE adoption affects the grid or how greening industrial heat impacts power demands, we're just operating with an incomplete picture. This isolated focus, it really represents a significant research gap in understanding those cross-sectoral links, the synergies and dependencies that are absolutely essential for a robust system.
And it looks like many studies are also overlooking the wider societal economic stuff, too. Carbon pricing, for instance, only showed up in 412 out of over 1,000 studies.
Less than half, yeah.
And get this, job creation was mentioned in only 45 studies, 45.
Wow, that low. That's a really stark finding. It really highlights a disconnect, doesn't it, between the purely technical energy modeling and the broader socioeconomic realities.
Definitely.
Because technical feasibility is obviously vital. You need that first. But the actual implementation, the societal acceptance of these huge transitions, that's going to depend heavily on things like policy, economic viability, the impact on jobs.
Public support.
Exactly. And neglecting those aspects in the modeling just means we're getting an incomplete, maybe even an oversimplified view of whether these plans are actually viable in the real world.
Okay, let's shift from how they model to what they're modeling. Looking at the actual technologies, who are the undisputed champions, the ones leading the charge in power generation, according to this big review?
Oh, the study leaves absolutely no doubt there. Solar photovoltaics, PV, and wind power. They are the undisputed heavyweights.
The big two.
The big two, showing up in a whopping 94% of the articles. That's 1,001 studies for solar PV, 1,002 for wind. They are quite simply the backbone of a renewable future.
Why them specifically?
Right. It comes down to cost effectiveness, mainly, and widespread availability, scalability. They just tick a lot of boxes. Plus, we're seeing ongoing innovation, like bifacial solar panels getting more energy, and massive growth in both onshore and increasingly offshore wind. These two are the workhorses.
Okay, so solar and wind are the stars. What about the supporting cast, other technologies backing them up?
Right, there's definitely a supporting cast. Hydropower, that was in 58% of studies in bioenergy, in 62%, also play pretty prominent roles.
Okay.
And their usage, actually between 2020 and 2023, was incredibly active. The study noted 1.2 times higher adoption than in all the preceding years combined.
Wow, a real acceleration there.
Yeah, significant. Hydropower offers that flexible, dispatchable, low-carbon power, although it does have its environmental challenges, of course. Bioenergy is becoming increasingly important, especially as a sustainable source of bio-CO2.
Bio-CO2.
Yeah, for producing things like e-fuels and e-chemicals, which are really crucial for those harder to decarbonize sectors like heavy industry or aviation. But what's also really insightful is which renewable technologies get less attention. Geothermal energy, for example, appeared in just 25% of studies.
Only a quarter.
Yeah. Concentrated solar thermal power, CSP, that was even lower, just 14%. And ocean power that includes wave, tidal, and OTEC, which is ocean thermal energy conversion.
Right, the ocean stuff.
That was in only 12%. So this lower adoption, it's largely down to factors like, well, they're at earlier development stages, often higher costs or unique environmental constraints. But they still hold significant potential in specific regions.
And it seems there might be some missed opportunities even with established tech, things that aren't being fully explored in the research. The study points out only 18% of studies included rooftop PV prosumers.
Yeah, that's people like you or me generating our own power.
Right. Instead, the big utility-scale installations dominate the research, and things like offshore solar floating PV almost entirely ignored.
Virtually absent, yeah.
This really raises a crucial question. Are we maybe overlooking readily available, potentially cost-reducing options by focusing so heavily on these massive utility projects?
That's a really astute observation. I mean, distributed generation, like rooftop solar, it can reduce system costs, it can enhance local resilience, empower consumers,
Yeah.
yet it's significantly underrepresented in these models. And similarly, offshore floating PV. It holds immense potential, especially for places without much land. It could even integrate with offshore wind farms, share infrastructure, maybe cut overall costs. The research community might indeed be missing opportunities by focusing so much on the big centralized stuff.
Okay, so moving beyond just making electricity, a truly 100% renewable system needs to connect all the sectors, right? And given how variable renewables are, storage becomes absolutely critical for managing the grid. What does this study tell us about storage?
You're absolutely right. Storage is non-negotiable, and the studies reflect that mostly. A substantial chunk, 85.3%, included some form of storage.
Okay, that's good. What kind?
Batteries are the most common solution, appearing in just over 60% of studies, followed by e-hydrogen, that's in about 35%.
And hydrogen, okay.
Yeah, using renewable electricity to make hydrogen for later use. But other key ones are popping up too. Pumped hydro storage, PHES, that's the classic one. E-methane, which is like e-hydrogen but one step further. Thermal energy storage, TES. Vehicle to the grid, V2G, and compressed air energy storage, CAES. They're all gaining ground, and each offers, unique benefits for grid flexibility.
I found something really surprising about vehicle-to-grid, V2G, in this study. The whole idea using EV batteries to send power back to the grid that emerged as a recognized thing back in 2009.
Yeah, about then.
Yet the study says the first papers that actually crunched the numbers for all 7 of those storage options you listed in a single article, they were only published in 2023.
2023, that's recent.
It is. And apparently even leading research teams often leave out at least one of these options in their studies. What does that lag tell us about how complex this integrated modeling actually is?
Oh, that lag is incredibly telling.
Yeah.
It just underscores the sheer complexity of trying to fully integrate all these diverse flexibility options. It's hard work modeling this stuff holistically.
Right.
Each storage tech has unique characteristics,
Right.
Different durations, efficiencies, costs, understanding how they all work together, their combined synergistic effects. That's crucial for keeping the grid stable and cost-effective with high renewables. It's like trying to conduct an orchestra when you only have half the instruments. You don't get the full picture.
Makes sense. Okay, beyond electricity and storage, what about heating and transport, the other big energy users? How are researchers tackling those sectors?
Right. In the heat sector, heat pumps are definitely the leading technology. They showed up in 32% of studies. They're really valued for their efficiency, that coefficient of performance, or COP.
High COP. Yeah.
Exactly. District heating, GH, is also covered quite a bit in 22% of studies. That highlights its importance for integrating different heat sources and providing system flexibility, especially in denser areas.
And transport.
For transport, road is king in the research. It's the most assessed mode in 35% of studies. And within road transport, battery electric vehicles, BEVs, are dominant, especially for light-duty vehicles LDVs, cars, and small vans. BEVs featured in 92% of studies looking at LDVs.
92%, so a very strong signal towards electrification for personal transport.
A very strong, yeah, almost universal signal in the research for cars.
That's clear for cars. But what about the sectors that are much tougher to electrify? Like, real transport is mostly electric already, but you mentioned only 17% of studies looked at hydrogen for rail. And what about those really challenging, hard-to-abate sectors? Shipping, aviation, where batteries aren't really feasible for long distances. What are the key technologies there?
Yeah, that's where e-fuels really become essential. The research clearly shows that things like e-hydrogen, e-Fischer-Tropsch liquids, those are basically synthetic fuels made using green hydrogen and captured CO2.
Okay, synthetic fuels.
Right. And e-methanol, too. These are seen as pivotal for decarbonizing those big, heavy segments. They effectively act as energy carriers, right? You convert renewable electricity into a chemical fuel that can power ships, planes, maybe heavy industry, where batteries just don't cut it. It really shows the need for diverse sector-specific solutions.
Okay, now let's look at what the study calls the toughest nuts to crack. Industry, desalination, and critically, carbon removal. Industrial decarbonization, for example, seems to have gotten a slow start in these 100% RE analyses.
Well, it certainly did. The industry sector was, largely overlooked in these kinds of analyses until about 2021. Interest is definitely growing now, though.
Okay.
Often, industrial process heat gets included, but sort of generically. Specific industries, though, like iron and steel, they're in about 13% of the industry articles and chemicals, and 17% they're starting to get more focused attention.
But some are still lagging.
Definitely. What's particularly surprising is the pulp and paper industry. It's hugely energy and water intensive, but it's among the least studied. Yet, it offers significant potential for capturing bio-CO2, which, as we said, could then feed back into making e-fuels and e-chemicals, a missed synergy perhaps.
And desalination, getting fresh water from the sea, also limited focus.
Also limited, yeah. Seawater reverse osmosis, SWRO, is clearly the main method being looked at. It's in 90% of the desalination studies, that's driven by tech improvements and falling costs.
Right.
But the overall low focus on desalination itself is quite a significant gap, especially when you think about growing global water scarcity. There's this inextricable link between water and clean energy, the energy-water nexus. As populations grow and fresh water gets scarcer, integrating clean energy with desalination is going to become ever more critical.
That brings up a really crucial point. We hear constantly that hitting the 1.5 degrees C climate target likely needs net negative CO2 emissions.
That's the scientific consensus, yeah.
So why are carbon dioxide removal options, CDR, so underrepresented in these studies? Bioenergy with carbon capture and sequestration, BECCS, only 1% of studies. Direct air carbon capture, DACCS, even less, 0.7%.
Tiny fractions.
And other essential CDR options like enhanced weathering or planting forests, virtually absent. What are the implications of leaving these out so often?
It's a critical oversight, honestly, and one that needs urgent attention from the research community. The science is clear. We need to actively remove CO2 from the atmosphere to meet those ambitious climate targets. Yet these vital technologies are barely integrated into these 100% RE system models.
So the models might be too optimistic.
Well, it represents a significant research gap and a potential blind spot. If we're not fully accounting for these necessary negative emissions pathways, our models might be underestimating the true scale of the challenge. Or worse, they might be suggesting technically feasible paths forward that simply aren't sufficient to stabilize the climate.
Okay, zooming out even further now. The study also highlights big global disparities in where this research is happening. What does the geography tell us?
It tells us a lot about where the focus currently lies and where it maybe doesn't. Germany leads the pack as the most studied country in the day. 81 articles focused just on Germany. Then Denmark, the USA, Australia.
Okay, developed economies mostly.
Predominantly, yeah. Europe as a whole accounts for a massive 45% of all this research. But in stark contrast, regions like Eurasia, think Central Asia, Russia, Africa, Southeast Asia, they're significantly underrepresented. Eurasia, for example, only accounted for 1% of the articles. 1%.
Wow, only 1%. That's a huge imbalance.
It is. And this geographical distribution, it often doesn't line up with where the global energy transitions are actually most critical or where they could have the most profound impact, positive or negative. This imbalance could easily lead to solutions that are biased towards certain regions or just a lack of attention to the unique challenges and opportunities in those less studied areas.
And I guess reflecting those geographical differences, the study notes that specific technology preferences seem to be emerging by region.
Precisely. It's logical to some extent. Solar PV is, perhaps unsurprisingly, more prominent in regions with high solar irradiation. India, Italy, Japan.
Makes sense.
Wind power, conversely, thrives in the analysis for wind-rich areas like Denmark, Germany, the USA. Heat pumps are widely adopted in many models across different regions, but interestingly, in India, the models favor direct electric heating twice as much as heat pumps.
Oh, interesting. Any universal trends?
One stands out, light-duty DEVs, so electric cars. They're the predominant road transport solution modeled across all regions. That signals a pretty strong global consensus, at least in the research community, on electrifying personal vehicles.
Okay, finally, the study makes this rather stark conclusion. When we compare these ambitious future projections from the models with what's actually happening on the ground, the study says these projected outcomes often fail to align with real-world developments. What does that mean for how fast we're actually moving?
Yeah, that's a bit of a reality check, isn't it? It means there's a significant and frankly concerning lag. The study points out that current regional electricity mixes show fossil fuels still dominating over 75% in places like the Middle East, South Asia, Africa, as recently as 2020.
Still over three-quarters fossil fuels.
Yeah. And while the future projections for, say, 2030 often show these really ambitious pathways towards renewables, the actual implementation of net zero targets just isn't keeping pace. This gap, it really highlights the urgent need to accelerate deployment, get these technologies built, and critically align policy and investment with the ambitious pathways that the research is outlining. It's like we have the maps, but we're not driving nearly fast enough.
This deep dive into technologies, trends, and trajectories reviewed in 100% renewable energy system analyses has really uncovered a lot. A rapidly expanding field of research, yes, but also quite uneven.
Definitely uneven.
We've seen that clear dominance of solar PV and wind, the absolutely critical role of sector coupling and diverse storage, but also these persistent gaps, right? In fully integrated analyses, in geographical balance, and in covering all sectors comprehensively, especially tricky ones like industry desalination and those vital carbon dioxide removal technologies.
Key gaps, yeah.
So what does this all mean for you listening? Well, for policymakers, it seems like a clear call to action. Align that infrastructure investment, the regulations, with integrated multi-sectoral strategies,
Yeah.
and tailor them to local contexts.
Absolutely. And for innovators, for researchers, it really highlights these crucial areas that are currently under-examined but could hold immense potential for breaking new ground in the energy transition. Lots more work to do. And maybe a final thought to leave people with. As we pursue these 100% renewable energy systems, this study really challenges us all to ask, are we focusing enough on the entire puzzle? From the smallest village right up to global industries. And maybe more urgently, are we moving fast enough to bridge that gap between the research ambition and the real-world implementation needed to secure a truly sustainable future?
A critical question indeed. That was our deep dive into technologies, trends, and trajectories reviewed in 100% renewable energy system analyses. Thank you for joining us.